Hello, I'm Lorenzzo Mantovani, and I'm going to talk about shooting against unsafe evaluation of shielded deep reinforcement learning approaches for autonomous spacecraft. First, what is the Agile Earth Observing Spacecraft scheduling problem? And here, this sort of spacecraft, they are useful for crop monitoring, disaster response, and intelligence gathering. The issue is that the demand for the systems is much larger than what they can fulfill, and this leads to the oversubscribed problem. And then we have the Earth observing satellite scheduling problem, which is basically determining the sequence of tasks that the systems will perform to maximize the mission outcome while being subjected to system constraints. Traditional methods to approach this problem, they consider heuristics or optimal solvers. But the issue is that they tend to be slow, require large compute power, or they are hard to develop or change for a specific instance of the problem. And because of that, the plan is usually generated on the ground and uplinked to the spacecraft, making it difficult to react to short-lived events, new targets that are arriving dynamically, uncertainty that's impacting the environment, or even any change that you have. So because of that, there's growing interest in onboard autonomy. And one way to provide autonomy is using deep reinforcement learning. It has shown potential for fast onboard retasking and closed loop decision making. So the motivation for this work is even if you have these autonomous systems, these policies that are running on board spacecraft, you have safety concerns. And you can use shields to provide extra safety layers. Shields are mechanisms that are wrapped around the policy. But with that, how much performance are we losing by incorporating these shields, and how can we have a better synergy between shields and these policies? Prior work, they looked at different ways of incorporating shields during training, but they were usually limited to simple environments or games. So the shields were studied in the context of the Agile spacecraft scheduling problem, but they didn't really look at different methods to train with shields. So the motivation and the contribution here is to compare different ways to train with shields in this specific sort of problem that we are interested at. And what we notice is a small trade-off in performance and safety on the long run. But how did we reach that conclusion? First, we need to formulate the decision-making problem. So for that, we use a Markov decision process. We have the state space that has information about the environment, the spacecraft, an action space that are the actions that are available to the agent, transition function that determines which state the system is going to move to given the current state and action, reward function, and the discount factor. And the goal here is to find a policy that's mapping the current state to the action space. So basically, given your current state, which actions should you select that maximizes the expected sum of discounted reward. And the problem we are looking at is a satellite in a circular orbit that's trying to maximize the number of targets that it's imaging weighted by their priorities. But it's subjected to battery and reaction wheel speeds as safety constraints. So if the battery charge reaches zero, it reaches a terminal state. Similar thing if the reaction wheel speeds exceed some certain limit. The agent has 35 actions available. 32 of those are imaging actions, such that it can select any of the upcoming 32 targets to image. And it also has the charge action, downlink action, and the set action that bring the reaction wheel speeds down. We train these agents using 3 orbit long episodes. So every 3 orbits, we reset the environment with randomized initial conditions. That is useful to expose the agents to more parts of the state space. But since we were interested in the long-term performance and safety considerations, we tested them in 90 orbit long episodes. The issue with these very long episodes is that even if you have a few thousand targets to image, soon you will run out of targets. So to avoid that, we started adding targets from time to time to these environments, and that also highlights how these policies can adapt to these changing requests. So we use deep reinforcement learning to solve this problem, such that parts of the problem are replaced with deep neural networks. And we implemented all these in BSKRL. BSKRL is an open source Python framework for spacecraft scheduling studies, and it combines Basilisk, which is high fidelity, fast, and with flight-proven software, with Gymnasium. Gymnasium is providing this standard interface for reinforcement learning studies. While talking about shields now, shields are these mechanisms that help provide safety, and they can be constructed using heuristics, so expert knowledge of the problem, such as this handcrafted one. And for example, you can say, well, if your battery charge level is below 20%, you should charge. The issue with this method is sometimes it's hard to account for edge cases and have really guarantees on the safety it's providing. Instead, you can use shields constructed with formal methods. Here, we are using the Q-optimal shield that was developed by Robert Reed and Dr. Lahijanian, and it basically obtains a safety MDP from the original Markov decision process, and it's solved using dynamic programming such that you have a probability of staying safe if you follow the policy that is returned by this shield. With that, we have different ways of incorporating the shields in training. One way is action replacement. Basically, the observation will go through the action, the agent, and the agent will sample one action. This is the original action. And that goes through the shield. And the shield will determine if that action is safe or not. If the shield determines that it is an unsafe action, it will replace that with a safe action that will interact with the environment. We can couple that with interference penalties. So every time the shield has to swap that original action with a safe action, it also returns some penalties to the agent. Another method is action masking. And we take those shields and use them to create masks such that the agent cannot sample unsafe actions. It only selects safe actions that will interact with the environment. So we compared these different methods with a few baselines. And for baseline, we had the case that was trained without any shields and without any failure penalty, and one that was trained with -10 for reaching a terminal state. And this is from prior work. Action replacement, we also investigated different levels of interference penalties, and action masking is just pure action masking. Okay, what about the training results? How these agents behave during training? So we have a few cases here. Action replacement, we have pi1, that's our baseline without any failure penalty. We have pi infinity. This is actually an upper bound. Imagine that we just took that satellite and gave it a very large battery and no reaction will speed constraints. We also have the action replacement with different levels of interference penalties ranging from 0.01 to 10, and also the action masking with both shields. This is a lot, so I want to bring your attention to very specific things. First, we can look at the top plots, rewards as a function of training steps. And what we see is that all cases here, they are improving over the course of training. So using those shields and those methods to incorporate shields is not hurting performance. We can also look at shield interference during training. What we see is that all cases are, in all cases, it's decreasing over the course of training. And the case with the least interference is the one with action replacement with interference penalties. Now, if we look at that specific case more closely, we see that increasing that interference penalty leads to decreased shield interference. And that is expected, as the agent will try to avoid that or those actions, those unsafe actions more actively. We can also look at that in terms of rewards, but here increasing that interference penalty is not necessarily leading to an increase in rewards, because that is leading to over-conservative policies. So there's some sweet spot in terms of the interference penalty that you should use. What if we take this policy that we trained and now test them under different conditions? So first, let's look at the policies that were trained without any shields. We have our baselines in here. So we took them and tested without shields in those 90-yard long episodes, have many test cases here. And what we notice is that most of the agents are not alive after 90 orbits. So they are having a hard time learning the safety constraints and staying alive. Well, on the other hand, we can take the policies that were trained with shields and also remove them just to look at how they behave. And what we notice is that even without those shields, some of these cases are much better at staying alive. Specifically, the cases that are better are those that were trained with interference penalties of -1 and -10. This is about learning the safety aspects of the problem, but what we are really interested at is the safety performance trade-off when using those shields and on the long run. So let's look at that. Here, I took two policies. I took the policy that was trained with the handcrafted shield and -1 for interference penalty, and policy was trained with the Q shield and also -1 for interference penalty. But in these two cases on the left, those two green lines, I removed the shields for testing. And those two on the right are just tested as they were trained with the shields. And what we notice here is that the green lines are below the other lines, meaning that the unshielded cases are performing worse than the shielded agents. And the main reason behind this is that not all of the unshielded agents are alive at the end of those episodes. Only between 54 to 63% of them are alive. So instead, we can look at what we call elite cases. Let's remove all cases or all agents that died during the episode. We only consider those that survived the whole episode. And what we notice here is that all lines are overlapping. What that's telling us actually is that on the long run, these shielded agents are performing comparably to the unshielded agents, with the main difference being that 100% of the shielded agents are alive, whereas only 54 to 63% of the unshielded agents are alive. So the main thing here is that this performance safe trade-off decreases with longer episodes, and we see that these agents are actually performing comparably. The best performance that we saw was using action replacement with interference penalty, and that also led to less reliance on shields during testing. Increasing that interference penalty ended up leading to over-conservative behavior, and masking overall tended to perform better than action replacement, but when we didn't account for the interference penalties. And these results are consistent across the two different shields that we tested. Thank you for your attention.